Welcome to Unit 3, Trigonometric Functions. We are going to take an amazing ride, an amazing journey through the wonderful world of inverse trigonometric functions. Inverse trig functions are extremely powerful, extremely useful, and very easy to work with if we just take a couple moments to understand them. So get ready for a crazy ride here. All right, so before we can even begin to understand inverse trig functions, we really need, for maybe the third time, I don't know, really need to focus on what the heck a regular trig function is. So again, to really understand inverse trig functions, we have to truly understand inputs and outputs of trig functions. So again, inputs, which are commonly called x in functions. I mean, 99% of functions, the input is an x. But in trig functions, that x represents an angle. Okay, we understand that. And again, officially, we like to use radians. Okay, that should all make sense. And the output, which usually we do call the y, and again, in 99% of functions, the output is the y value. So the output, the y value of these functions, well, what that represents depends on what trig function you're working with. So if you're working with sine, the output is the y coordinate on the unit circle where the angle stopped. So the angle that you plugged in tells you where to look on the unit circle, or where to stop, or where to terminate on the unit circle. And where you terminate is the y coordinate, and that is the value for sine. That's the output. For cosine, the outputs are the x coordinates on the unit circle where the angle stopped. So you find where the angle stopped, yeah, the angle you plugged in as the input, and you look at the x coordinate, and that is your cosine output. Tangent, the outputs are the x coordinate divided by the y coordinate divided by the x coordinate on the unit circle where the angle stopped. So it's important to know that the number one rule, the number one definition of a function is that every input can only have one output. So when I plug in an angle, there can only be one output. So when I plug in an angle, let's say pi over 6, I better only have one y coordinate at pi over 6. That's sine, right? If I'm going to have 2 or 3 y coordinates, well, that's not a function. Same thing with cosine. When I plug in an angle, say 32 degrees, I know that's degrees, but you could still plug in degrees. Again, when I plug 32 degrees in, the only output is the only one x coordinate from that point. So each input has one output, right? I mean, that's a definition of functions. So those outputs are repeated, though. Again, you are allowed to have multiple outputs. Well, I take that back. The way I said that didn't sound right. Each input's only allowed one output, but you could have outputs that are repeated. For example, you could have 2, 3, 4, 5 different angles that all produce the same output. But again, each one of those angles is only one output. So here are those functions, right? This is beautiful function notation. F of x equals sine of x. And again, all I'm asking that you remember is that this input right here, x, is an angle. This output right here we call y is a y coordinate from the unit circle where this angle stopped. Same thing here for cosine. This is an angle. That's really the key thing I want you to remember. But again, this y, this output, is the x coordinate on the unit circle where this angle stopped. And then for tangent, this x, again, is an angle. You plug in an angle, and this outcome is the y coordinate divided by the x coordinate from the unit circle where this angle stopped. So I know that you're like, why is he repeating all of this? We've learned this several times, because I have found so many times that kids get this far and still don't truly understand this. I think it's very valuable to take the time to go over this multiple times. So let's actually look at a couple of examples. So here are several different trig functions, and I have some input values. So here we're inputting 3 pi over 4. So again, that's an angle. So we find that angle on the unit circle. Here it is right here. And it terminates right here at this point. And again, sine wants the output as the y coordinate from the unit circle where 3 pi over 4 stopped. And that y coordinate is radical 2 over 2. Easy. Input, output. So simple. All right, 5 pi over 6. All we got to do is find 5 pi over 6. And it's right here. There it is. This is the place where 5 pi over 6 stopped on the unit circle. And then we got to remember cosine. The output of cosine is the x coordinate where that angle stopped. Negative radical 3 over 2. Input, angle, output, x coordinate. So easy. All right, tangent. So we have 4 pi over 3 here. So the first we got to do is locate 4 pi over 3. There it is. And then we got to remember that this is where it stopped. And tangent wants the y coordinate negative radical 3 over 2 divided by the x-coordinate, negative 1/2. But of course, instead of dividing by the fraction, I'm going to multiply by the reciprocal, negative 2 over 1. 2's cancel, negatives make a positive, and I get radical 3. Output from this input. Now, I want to emphasize the rule, right? If I plug 4 pi over 3 in again to tangent, I'm going to get radical 3. I can't get anything else. As long as I do my work right, the input of 4 pi over 3 led to one output, radical 3. That's it. All right, sine of 11 pi over 4. Now, if I look on the unit circle, I don't see 11 pi over 4. So I got two choices here. One, maybe this is an angle that's just not a beautiful angle. Well, in that case, you could use your calculator. But anytime your denominator is 6, 4, 3, or 2, trust me, it's on the unit circle. So 11 pi over 4 is on the unit circle. I must just have to count to find it, or I could find the coterminal angles. So if I go all the way around the unit circle, that's 8/4 pi. 8/4 is 2 pi. So this would, if I keep going, this would be 9/4, 10/4, 11/4. So 11/4 would actually be equal to 3 pi over 4. Now, if you don't like counting, then you could just subtract. So 11/4 pi minus 8/4 pi. 8/4 is the same thing as 2 pi. All I'm doing at this point is finding coterminal angles. And 11 pi minus 8 pi is 3/4 pi. So once again, I'm at 3/4 pi. And this time I want sine. Well, sine is the y-coordinate, radical 2 over 2. So notice, what I want to take a moment to notice here is that earlier we already did sine of 3 pi over 4. And we also got radical 2 over 2. But 3 pi over 4 and 11 pi over 4 are different inputs. They are technically different angles. But since they have the same terminating spot, therefore the y-coordinates are the same, radical 2 over 2. So this is a good example of two inputs that led to the same output, which by definitions of a function is totally fine, as long as 11 pi over 4 input doesn't have any other outputs, then I'm fine. All right, so let's do one more here, negative 13 pi over 6. Once again, if you don't like working with fractions, I'm sorry. Got to. So 13 pi over 6, we could add 12/6. Why 12/6? Because that's 2 pi. Just find the coterminal angle. And that's negative pi over 6. Now, that's, most kids can see that, because if this is positive pi over 6, this would be negative pi over 6. But if you want, you could add another 12/6. Just go around the circle again. And negative 1/6 plus 12/6 is 11/6 pi. So this is 11/6 pi. All right, and now I want the x-coordinate, because that's what cosine is. The x-coordinate from the unit circle is radical 3 over 2. All right, so what I'm doing here is just demonstrating exactly what functions are. Trig functions take in angles. You got to know where to look on the unit circle, and then the outcome is a cosine, x-coordinate of the unit circle, sine, y-coordinate of the unit circle, tangent, y divided by x. Now, again, there's plenty of angles that are not here. So, for example, if I ask you for cosine of 13 pi over 5, you're never going to find that. It's on the unit circle. It's just not one of our pretty exact angles. It's not one of our special angles, 30, 45, 60. Those are our special angles. So no big deal. Again, it's still there. You would just use your calculator. Just make sure you're in radian mode, or else you're not going to get it right, because this is in radians. And cosine of 13 pi over 5 is negative 0.309. Negative 0.309. So if I was able to see where this angle stopped on the unit circle, this would be the approximate x-coordinate. So again, we could actually try to find that. Negative 0.309 would be somewhere maybe right around here-ish, right? This is negative 1, so negative 0.309 would be somewhere right around here. So 13 pi over 5 would probably be somewhere in this vicinity. But again, don't worry about that, right? It finds it for me. Okay. All right, now we could also think about these trig functions through the eyes of a right triangle. Again, this goes all the way back to the beginning of what we learned about trigonometry. But I do want to emphasize this, that, trig functions can also be looked at as triangles. So, for example, sine of angle x. If I plug angle x into this function, if I plug an angle right here into sine, the output is the opposite m divided by the hypotenuse w, right? So again, input angle, output. This time, since I'm working with a triangle, the output is the opposite divided by the hypotenuse. It's that ratio. Cosine of angle x would be the adjacent divided by the hypotenuse. Again, so you could define the trig functions based on the unit circle, x-coordinate, y-coordinate, or you could define it based on a triangle, ratio of opposite over hypotenuse, adjacent over hypotenuse, and so forth. All right, so now that I truly hope that we do have a firm grip on trig functions, inputs, what they represent, angles, outputs, what they represent. Now we could turn our attention to inverse trig functions. Now, hopefully you learned about inverse functions maybe back in Algebra 2 or earlier in pre-calc, but inverse trig functions, or just inverse functions in general, all you do is you switch your x's and y's. That's it. That's what an inverse is. It's switching your x's and y's, switching your inputs and your outputs. It's really that simple. And we denote inverse functions with a little -1. So when you see this little -1, that represents an inverse function. Now, this gets a little bit confusing because exponents, for example, x to the -1, we have learned means that you move it to the denominator where it could have a +1. Yes, but this -1 that we're using right here is not talking about an exponent. It's not talking about, it's not an exponent that we move to denominator. And I know that that's confusing because I know that's what it looks like. That's what you're going to want to think. But inverse functions are denoted with a little -1. We'll even sometimes put them on the F as well to denote as a -1. So again, I know that that's confusing because you're used to seeing -1s as exponents and you understand what a -1 exponent tells you to do. But these are not exponents. This is representing an inverse function. So this is just a little superscript that represents, it's signifying this is an inverse function. So when you're working with inverse sign, and again, how do I know I'm working with inverse sign? I see that little -1. Okay. All that means that my input and my outputs are switched. So this is where we really got to focus. Now, my input is a y-coordinate from the unit circle. My output is an angle. And I know that that's very confusing, but I'm just asking that you understand that. That's literally what inverse functions are. They flip around. The input is a y-coordinate from the unit circle, where an angle stopped, and the output is that angle. So we're just flip-flopping those two values. So again, cosine inverse, notice that it's denoted by the little -1 right here. That's signifying that we are working with an inverse cosine function. And you have to understand what that means is that this input is now an x-coordinate from the unit circle, where an angle stopped. This output, which again is y, is the angle. So we're flipping, we're inversing, we're switching the x and y's, we're switching the input and outputs. So again, gotta be careful. Hopefully this is easy. You should have worked with inverse functions before. All right, so here is the last one. This is the inverse tangent. Once again, we denote inverse tangent with this little -1. I can't say it again. Don't confuse it with a -1 exponent. It's not what it is. All that's telling you is that my inputs and my outputs have now been switched. So this input is no longer an angle. This input is the ratio of a y-coordinate divided by an x-coordinate from the unit circle. And this output is an angle. All right, that's it. Yes, that's it. I told you, inverse functions really aren't that overly difficult. All you have to understand is when you say that little -1, it means that your input and your output are completely switched around, which might take a little bit of time to process, but once you do so through this video, I hope you'll understand it. And again, we're still going to need the unit circle for this because the unit circle is filled with x-coordinates, y-coordinates, and angles. We're just going to look at it in reverse. So let's look at a couple of examples here. So first example, how do I know this is an inverse function? I see that little -1. All right, this means that the input is no longer an angle. The answer is an angle. The answer is an angle. The input is a y-coordinate from the unit circle. So I'm looking on my unit circle, I'm looking for a y-coordinate. Oh, here's a y-coordinate that's 1/2. So maybe the answer is pi/6 because that is the angle that has that y-coordinate. Input is now a y-coordinate. Output is now an angle. But we do run into a problem because I actually see another place where we have a y-coordinate of 1/2. So maybe the answer is 5pi/6 because again, that would be an angle that has a y-coordinate of 1/2. Well, this is, excuse me, where we do run into a little bit of an issue that I'll address in a moment because the definition of all functions, even inverse functions, because they're still functions, is that you can only have one output. So right now I'm going to have to figure this out because I can't have two outputs, but I want you to understand that. All right, let's see this next one here. This is another inverse function. How do I know? I see that little -1. This time, this is not an angle, right? I'm switching that. So the answer is an angle. This is an x-coordinate. How do I know it's an x-coordinate? Because I'm working with cosine. So I'm looking for where do I see an x-coordinate of negative radical 3 over 2. Voila, here one is right here. There's an x-coordinate negative radical 3 over 2. So my answer is 5 pi over 6. That's the angle that produces that x-coordinate. But again, look down here, we see another place where this happens. So maybe the answer is 7 pi over 6. That's a problem, the fact that we have two outputs. Well, if you actually want to be honest, I could sit here all day and list outputs, because if once I recognize that 5 pi over 6 has that x-coordinate, I could just add 2 pi, add 2 pi, add 2 pi, and I'm going to continue to get billions of angles that have an x-coordinate of negative radical 3 over 2. So we are going to have to fix that problem, and we will in a minute, because we can't have functions with bazillions of outputs. We're only allowed one output. All right, let's keep practicing, though, just to understand. So once again, this is tangent inverse. How do I know? Because I see that -1. And this wants me to find an angle. Remember, in the output of inverses are angles. All right, so what's this 1 represent? Oh, that's a y divided by x. So where on the unit circle, if I do y divided by x, do I get 1? Look no further than pi over 4. Look right here. If I take y, radical 2 over 2, and divide it by x, radical 2 over 2, you get 1. When you divide the two numbers are the same, you get 1. So at pi over 4, I do have that as my answer. So again, the input was the ratio of the y divided by x. The output was the angle. But once again, same issue we've had earlier. I do see another spot where this happens, because at 5 pi over 4, I also have a y divided by x that produces +1. All right, now for this next one here, I can't use my unit circle because I don't see this on my unit circle. And again, first up, I got to recognize this is an inverse. That means my answer is an angle. Notice how I write that down to remind myself. My answer is an angle this time. So where do I see a y-coordinate of 0.98? Now, 0.98 is going to be right around here, right? So that's really, really close to 1. So we're looking probably right around here. We're looking at that angle. But again, that's not one of my beautiful, wonderful, nice, awesome, huggable angles on the unit circle. So I am going to have to go to my calculator. Now be careful when you use the inverse sign on your calculator. You're going to hit second sign to pull up the inverse sign. You'll see that little -1. But really focus on what mode you're in, because the answer you're going to get will be either degrees or radians based on what mode you're in. So since I've been giving all of my answers in radians, I do want to be in radian mode, so make sure I'm in radian mode. So when I do inverse sine of 0.98, it's going to give me an answer that's in radians, 1.37 radians. So my answer is 1.37 radians. Now, if you're interested in what degree that would be, well, you're more than welcome to switch modes to degree mode, and then do sine inverse of 0.98, and you get about 78.52 degrees, which actually makes a lot of sense, because that probably is roughly where I drew my angle right here, at about 78 degrees. But again, in radians, that's 1.37 radians. And again, those are both approximations, because the only way you get exact answers is if you're working with our beautiful angles. All right, so once again, you got to understand that little -1 indicates you're working with an inverse. So that means your answer is an angle. You just got to understand what's given. Sine, you're given the y-coordinate as the input. Cosine, you're given the x-coordinate as the input. Tangent, you're given the ratio of y divided by x. Now, we do have to address that issue, though, because to be a function, you're only allowed one and only one output. You can't have multiple outputs. So, for example, we just saw inverse sine of 1/2. We saw here that, pi over 6 and 5 pi over 6 both have a y-coordinate of 1/2. But again, I can keep adding 2 pi and adding 2 pi and even subtracting 2 pi. So if I leave it as it is, there's actually millions of answers to this. So the input of a y-coordinate of 1/2 has multiple answers. Yes, we see pi over 6 right away. We see 5 pi over 6. But if I just keep adding or subtracting 2 pi, I'm going to get more and more answers. And again, we can't have that. We just can't. To define this as a function, there's only allowed to be one output. So what we do to prevent this issue from occurring is we limit the inverse trig functions so that we only have one output. So this is where things get a little bit tricky, but it's meant to make it easier for you. That way you can't have 15 different answers. You only have one answer. So let's talk about how we limit these functions. So for inverse sine, we are only allowed outputs, and again, y is outputs. But I want you to understand that what are outputs of inverses? Outputs are y's, right? The output of any function is a y coordinate. But again, we're looking at angles, right? When we're working with inverse functions, the output, which we traditionally call y, the traditional name of an output for a function is y, but you have to understand, what does that represent in an inverse function? It represents an angle. So the inverse sine is only allowed to give answers that are from negative pi over 2 to positive pi over 2. So it's only allowed to look over here. And again, so this, I call it the no-fly zone. So this over here is the no-fly zone. You're not allowed to go through quadrants 2 or 3. You're not even allowed to go in or through. So that means that when you are given an inverse sine, you're only allowed to look up to pi over 2 or 90 degrees, or down to negative 90 degrees or negative pi over 2. So you're not allowed to look anywhere else. So now when I give you that problem, sine inverse of 1/2, the only answer you're allowed to give me is pi over 6. It's the only answer. The other answer that we saw was 5 pi over 6, but that's in the no-fly zone. Can't go over there. And you could say, well, Mr. Princhak, can't I just take pi over 6 and add 2 pi, add 2 pi? Yes, but if you add 2 pi, you go through quadrants 2 and 3, which you're not allowed to do. The only answers that are acceptable are up to pi over 2 or down to negative pi over 2. All right, so for cosine inverse, the angles that are allowed as outputs are anywhere from 0 to pi. 0 to pi. That's it. We're only allowed to look up there. So notice that x values do not repeat themselves. If I go from 0 to pi, I cover the full gambit of x values. Yes, they're all repeated down here in quadrants 3 and 4, but that is now the no-fly zone for cosine. You cannot go through those angles at all. So if I say, hey, what's inverse cosine of radical 3 over 2? You're going to say, where is there an x-coordinate of radical 3 over 2? Again, that's pi over 6 would be my answer. And that's the only answer. I'm not even allowed to add 2 pi to it, because then I go through the no-fly zone. I go through quadrants 3 and 4. Can't do that. All right, inverse tangent. Inverse tangent only has answers from negative pi over 2 to pi over 2. So it's similar to sine. Now, how come there's no or equal to signs here? Because remember, at pi over 2, tangent is actually undefined, because 1 divided by 0 is undefined. So we wouldn't even include those, because at pi over 2, tangent doesn't even make sense. Same thing with negative pi over 2, tangent does not make sense. Again, because negative 1 is the y, divided by 0 is the x, is undefined. All right, so this is how we allow there to only be a certain one output, right? For every inverse sine, cosine, tangent function. So you just got to remember, sine and tangent is quadrants 1 and 4, but again, it's really going up to pi over 2, down to negative pi over 2, and cosine is from 0 to pi. So those are the only place you're allowed to look. This is, I know that some kids are going to look at this as like more confusing. This is simply trying to make it easier to say, hey, there's only allowed to be one answer. Look where you're allowed to look and find your answer. All right, now one more thing before we look at a final couple of examples here is that in the old days, mathematicians used a different symbol, not simple, I should say symbol, sorry about that. I'm actually going to fix that right now. There, it was like it was always there. All right, in the old days, mathematicians used a different symbol for inverse trig functions. Don't ask why, not worth our time right now. I don't want to make this video longer than it needs to be. But we use that little -1 nowadays to represent an inverse trig function. But back in the old days, they called it arc sine. Arc cosine, arc tangent. So when you see that little ARC in front, it's arc, obviously. Arc sine is the old-fashioned way. That's how I say it, right? It's the old-fashioned way of representing an inverse sine. Arc cosine, inverse cosine, arc tangent, inverse cosine. So it's just an older format, so you will probably see that pop up. So if you see that pop up, don't be like, what the heck is this? It's just another indicator, kind of like my -1, that represents the inverse. It just alerts you to knowing that it's the inverse. All right, let's look at a series of examples here so that you can truly walk away understanding this. All right, This first example is arc sine. Remember, arc sine is meaning our inverse sine. So that means our answer is an angle. All right, so arc sine of 1/2. Now the input is a y coordinate. How did I know that? Because it's sine. And the output is an angle. So where do I see a y coordinate of 1/2? Well, I see it right here at pi over 6. But wait a minute, I also see it right here. No, sorry, you're not allowed to go over there for sine inverse. We're only allowed to go up to pi over 2, down to pi over 2. So this is the one and only one answer. All right, arc cosine of 1/2. So this is asking me again, arc means it's just an inverse. Just remember that. Don't let that confuse you. So again, this time the input is an x coordinate from the unit circle. The output is an angle. So where do I see an x coordinate of 1/2? I see it right here at pi over 3. So there's my answer. Now you could put 60 degrees, but I like radians. So make sure you read the directions. Sometimes it'll say radians, sometimes it'll say degrees. I do like to stick with radians. But once again, somebody might say, but Mr. Princhak, right here we also see an x coordinate of 1/2. Yeah, but not allowed to go down there for inverse cosine. Inverse cosine's only allowed to go from 0 to pi. All right, what about inverse tangent? Again, arc tangent is just a weird way of saying inverse tangent. Where do we see an angle that has a tangent of radical 3 over 3? So remember, tangent is y over x. I'm looking for where is the y divided by the x, radical 3 over 3. And let's see here. That's going to happen at pi over 6. Now, you're like, how did you know that so quick? Well, okay, I've been teaching this for 18 years. But again, if you do the dirty work if you have to, right? At pi over 6, you're going to take 1/2. You're going to divide it by radical 3 over 2, y divided by x. But instead of dividing, you're going to multiply by the reciprocal, 2 over radical 3. The 2's cancel, and we get 1 over radical 3. But we don't like radicals and denominators, so we'd multiply the top and bottom by radical 3, and we'd get radical 3 over 3. That's how I knew that's where it happened. All right, cosine inverse. This is, again, seeing that little -1. That's the inverse. Answer is going to be an angle. All right, so what is this? Well, cosine, that's an x-coordinate. So an x-coordinate from the unit circle. Where do I see an x-coordinate of negative radical 3 over 2? Right here at 5 pi over 6. Yes, I realize that it happens down here as well, but you're not allowed to go down there if you are inverse cosine. All right, arc tangent of negative radical 3. All right, this one's going to be a little bit tricky, okay? So listen and pay attention. All right, so first off, arc means inverse. That means I'm looking for an angle. I'm looking for an angle where the y divided by the x is negative radical 3. All right, well, let's see here. Well, that's going to happen right here at 5 pi over 3, right? Because, again, take the y coordinate, negative radical 3 over 2, divide it by the x coordinate, 1/2. Instead of dividing, multiply by 2 over 1. 2's cancel, and I get negative radical 3. And you might say, well, but wait a minute. Doesn't that happen right here as well? Yes, it does. But remember, tangent and sine are only allowed to go up to pi over 2, down to negative pi over 2. So what most kids are going to do is they will recognize that this is not the answer because it's in the wrong area, and that's a good thing. But the other thing kids will do wrong is they'll tell me the answer is 5 pi over 3. That is incorrect. The answer is not 5 pi over 3. Because 5 pi over 3 starts in quadrant 1 and goes all the way through quadrants 2, through quadrants 3, and then it lands in quadrant 4. Listen, that's what I'm trying to say. Sine and tangent are only allowed to go up to pi over 2, down to negative pi over 2. They're not even allowed to go through quadrants 2 and 3. So I'm not allowed to say 5 pi over 3. I have to give the negative angle, which would be negative pi over 3. There is my correct answer. Remember, negative pi over 3 is coterminal to 5 pi over 3. But I have to give that angle because remember, I already said to you guys, tangent is only allowed to give answers from negative pi over 2 to pi over 2. 5 pi over 3 does not fall in that, right? We're only allowed to go up to pi over 2, down to negative pi over 2. So if the answer is 5 pi over 3, that is the answer, but I have to go down to get there, which is negative pi over 6. I'm going to tell you, negative pi over 3. I'm sorry, negative pi over 3. Can't tell you how many kids mess that up, so you got to be super careful with that. All right, inverse cosine, arc cosines and -1s. That's an inverse. Inverse cosine of -1/2. My answer is an angle. I'm looking for an angle that has an x-coordinate of -1/2. Boom, 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 bing. There it is right there at 120 degrees or 2 pi over 3. 2 pi over 3 is my answer. Yes, I know there's another place right here, but that's not allowed to be there for inverse cosine. All right, inverse sine of radical 3 over 2. My answer is an angle. That's how I know when I see that little -1 or I see that arc. All right, this is a y-coordinate. How do I know it's a y-coordinate? Because it's sine. So where do I see a y-coordinate of radical 3 over 2? Beep, 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 right here at pi over 3. There's my answer. How easy is that? All right, inverse tangent of 0, looking for an angle. But what does this 0 represent? It represents y divided by x from the unit circle. So where do I see the y divided by the x being 0? Well, that happens right here. Y divided by x is 0. And that happens at 0 radians. Now, I know 0 radians is the same thing as 2 pi, but I'm not allowed to say 2 pi. Remember, tangent's only allowed to go up to pi over 2, down to negative pi over 2. Whew. All right, so hopefully you understood that. Hopefully you processed that. I'm telling you right now, you got to be super careful with like this problem I just did right here, the arc tangent of negative radical 3, because you see the answer and you want to say 5 pi over 3 so bad, but remember, you're not allowed to go around to get there. You got to go down. All right, now, where else could we use these inverse trig functions to really help us? Well, remember, what do inverse trig functions do? They give you an angle. The output's an angle, so we can actually use them to help us find missing angles in triangles. So if I'm asked to find the angle x in this triangle, the first thing I'm going to do is say, okay, well, 15 is opposite, 24 is hypotenuse, so that's sine. So sine of angle x equals opposite over hypotenuse. But I want to find the angle x. So to do that, I call it the old switcheroo. I literally want to switch my input with my output. Well, to do that switch, we need inverse functions, right? So I'm going to now switch the 15 over 24 inside the inverse sign, and the answer is my angle. It's called the old switcheroo. All you got to do is switch your input and your output, and when you make that switch, you got to use an inverse function. So now this is a triangle, so it would make sense to be in degrees. So I'm actually going to put myself in degree mode on my calculator. I'm going to do an inverse sine, so second sine of 15 over 24. And when you do an inverse, the output is an angle, and the angle is 38.682 degrees. 38.682 degrees. That is this angle. That angle, 38.682 degrees, that is the angle whose ratio of opposite divided by hypotenuse is 15 over 24. So easy. I mean, I can't make those any easier. All you got to do is pull the old switcheroo. If you're looking for the angle, switch your input and output. But again, need to use an inverse to make that happen. All right, let's look at 2 more examples of doing that. But this time, there's an unknown. There's an x. So this is actually trying to connect to what we did last unit with creating functions. So for each triangle, I want to write theta as a function of x. So remember what that means. I want to write theta as a function of x. So I want an equation for theta, and on the other side, I'm only allowed to have an x. So that's what we mean when we say write it as a function of x. So I want to know what is theta, but because there's an x involved, you're not going to give me a solid numerical answer. You're going to give me an answer that has an x in it. All right, so I'm literally going to do what I just did. All right, here's the angle I'm looking for. X is opposite, 4 is adjacent. So that's tangent. Tangent of theta equals x over 4. But I want a function for theta. So I'm going to pull the old switcheroo. I'm going to switch, but when I switch, I have to use an inverse. X over 4 equals theta. That's it. How easy was this problem? That's it. I'm done. All I had to do was figure out the traditional trig function and pull the old switcheroo to get an equation for the angle. So now if x is 5, I could plug it in right here and I could find the angle. If x is 12, I could plug it in right here and get the angle. If x is 32, I could plug it in right here and get the angle, right? Because now I've created a function where you plug in x and I will tell you the angle. All right, let's do one more here. X plus 3 is just a number I don't know yet. 2x is just a number I don't know yet. This is the adjacent. 2x is the hypotenuse, so I'm of course going to use cosine. cosine of the angle theta equals adjacent over hypotenuse. Now I want to pull the old switcheroo because I want theta. I want to know what theta is. So I'm going to do an inverse cosine of x plus 3 divided by 2x equals theta. So there it is. I created a function that tells me what theta is in terms of x. So if I whisper into your ear, x is 5, this becomes 10, this becomes 8, and I would plug 5 in here, I'd plug 5 in here, I'd get 10, I'd get 8 over 10, I would do an inverse cosine of 8 over 10, and voila, I would know my angle. Or maybe a birdie whispers into my ear, x is 12. Okay, the hypotenuse is now 24. The adjacent side is now 15. I would plug 12 in for x, and I would get 15 over 24, and I would do an inverse cosine, and voila, I would get my angle. So again, this is a function that finds angles, and all you had to do was pull the old switcheroo. Whew, all right, a little bit of a longer video, but guys, that is it for understanding inverse trig functions. Hopefully it all makes sense to you. Lots of moving pieces there. The key thing that you really have to hone in on is those restrictions, because inverse functions are functions, so I'm only allowed to have one output. So to prevent there from being a plethora of outputs, we have to limit the outputs for sine, cosine, and tangent so that there's only one output possible. Just be very careful with that. All right, good luck at doing your practice problems.